Welcome to Lesson 5 from Chapter 7, Trigonometry and Modelling from Year 2 Pure Maths. And today we're going to go back to proving identities. So we're going to do quite an exploration into identity problem solving using the trig identities that we've met so far. So we can go straight into it. There's 4 warm-up questions for you to try. So please pause the video and have a go at them. Okay, and let's have a look at the solutions. So the first warm-up question, we're asked to make a suitable substitution. You'll see this phrase quite regularly, suitable substitution, i.e. a substitution that will work is the short answer. And it says to make the substitution in the numerator on the left hand side. Now that's something you won't be told. This is just because this is a warm-up activity. So it's telling you to make a substitution for 1 subtract cos squared x. Now if we think about an identity that actually contains 1 subtract cos squared x, you might be thinking about double angle identities perhaps, or compound angle formulae. But the most obvious one, and the only one that really works, those ones I just mentioned were in fact red herrings, of course. So sine squared x plus cos squared x is identical to 1. And it's a case of, when you're doing these exercises, is being really, really mindful of your identities. It's a good idea to learn them and have them on hand so you can see how they've been manipulated in the question. So we can see here the manipulation is, of course, that we've subtracted cos squared from both sides of this. So if I rearrange it, we're going to have sine squared x is identical to 1 subtract cos squared x. All right. Now you might be thinking, well, how did I know to pick that identity? Well, there's another way to look at it, isn't there? This is using the left-hand side. So I'm just focusing purely on the left-hand side here. Now, what I could have done is maybe done a bit of rough work on the right-hand side. So is there a way I can kind of reverse engineer this, go back a couple of steps and see if I can see where I want to end up? Well, I can, particularly in this instance, because I know that tan squared is, of course, sine squared x over cos squared x. It's another identity from year 1. Okay, and now you can see that if this is to be true, then the 1 subtract cos squared x here must correspond to the sine squared x here. All right, because the cos squared x is also match. So that's another way to look at it. If you just maybe do a little bit of rough work on the right hand side and see if you can find maybe a meeting point for where the left and right will coalesce and maybe show you the answer. So that's another way to think about it. So to finish this off, obviously, all you need to do now is, if I take this information here, I can replace the 1 subtract cos squared with sine squared x like that. And I'm dividing by cos squared x, of course. Okay, and this is an identical. I'm working on the left-hand side. And that, of course, is the same as tan squared. And there wasn't really a lot to do in that one, and you could probably write down the answer, but I just want to emphasize some of the thought processes that go on when you're proving these identities. So that's the right-hand side. So we've done. Okay. Warm-up question 2 now. Another identity to prove, and we have something that looks rather complicated. And again, it's a case of spot the identity. If you went sort of without thinking too much about it, or if you weren't too sure about your identities, you might be tempted to do some kind of like expanding brackets maybe, and using the usual methods. But if you did that, of course, you'd be wasting your time. If you know your identities and you can spot them, you'll see very quickly that all this here can be replaced with 1. So that's really handy. All that is just absolutely identical to 1 for all values of theta. Okay, so then if we work on the left-hand side now, we can just say the left-hand side, well, that's just going to be identical to 1 plus cot squared theta, because we've used sine squared theta plus cos squared theta is identical to 1. And if you know your other identities, you'll know that 1 plus cot squared is, of course, cosec squared. Okay, which is the right-hand side. So we've proved the identity. Okay, so that's one of the reciprocal Pythagorean trig identities that we learnt in chapter 6. Okay, so that's questions 1 and 2. In question 3, we're going to continue the theme of spotting the identity. Now, let's have a look at what we have. Well, we've got cos squared, but we have 1 plus tan squared. And I'm going to focus on this for a second. And it's the same idea as question 2. Is there an identity we can replace, or is there an identity we can use to make a substitution for 1 plus tan squared theta? Indeed, there is. Now, you'll remember, hopefully, when you did your chapter 6 reciprocal Pythagorean trig identities, you'll remember that sec squared theta is identical to 1 plus tan squared theta. Okay, so that's really handy. That means I can replace this with sec squared theta. Okay, now why does that help us? What's special about sec squared theta? Well, let's go through the steps and you'll hopefully see if you haven't spotted it already. So go down here. So the left hand side, that's identical to cos squared theta multiplied by 1 plus tan squared, which is of course sec squared theta. And another recommendation when you're proving trig identities, although it doesn't always work, is to break all your trig ratios down, if you can, into their basic sine and cosine elements. So think of like sine theta and cosine theta as building blocks of your identities. Now, if you know that, you'll know very quickly that the left-hand side is now going to be identical to cos squared theta, but sec squared, if we use the third letter rule, of course, is 1 over cos squared. So it's in fact cos squared theta. Oops, I want the highlighter. Okay, so that's going to be 1 over cos squared theta, like that. Okay, now we have cancellation. So we can see quite clearly cos squareds are going to cancel. And our final answer is just going to be 1, which is the right-hand side. So again, that seems to have worked. What you're not allowed to do, of course, is to rearrange any of the original identities. So this identity has to remain in that form. You cannot manipulate it by maybe, I don't know, dividing both sides by cos squared or things like that. You have to take the left-hand side and show that the left-hand side is identical to the right, okay, or vice versa. Now, question 4. Again, excuse me, we're told to make a suitable substitution here. Now, this time in the denominator of the left-hand side. So we're told to make a substitution here. You won't normally be told that. It will just be a case of identity spotting. So is there an identity that we can use for this? And if you're not familiar with your identities, you might be thinking, isn't that cos squared A? Well, the answer is, of course, no. But there is a similar identity. Now, This, if you recognize it, is a double angle identity. Okay. And where is the clue in all this? Well, if you didn't know that was a double angle identity, you could infer it because on the right-hand side, you've got tan 2a. Okay, and if we do a little bit of reverse engineering again, if I just say, okay, what is tan 2a identical to? Well, that would be sine 2a. Let's rewrite that. Sine 2a over cos 2a. Yeah, it doesn't matter that it's 2a, okay, as long as you're consistent, that angle, whatever, it can be called anything you like, as long as it is replicated throughout the identity, which of course it is here and here, so that's fine. And you can see that the sine 2a corresponds to the sine 2a here. All right, so that means that the denominator must correspond with the cos 2a, and it does so directly via this identity, which I recommend you learn, okay, along with all the other ones. So that's going to be our thought process. So we just have to write it all out now. So the left-hand side is going to become sine 2a, and then I use my identity straight away over cos 2a. All right, and you can again use the tan identity now, and that's going to be tan 2a as required. And there we have it. So let's go straight into the worked examples with worked example 1, and we have to prove this identity. Now, just before we begin, there's a few things you might want to consider here. Notice we've got a cot squared here. We've got a cosec squared. I'm just going to highlight these in different colors, and we've got a cos 2x here. All right, so they're all kind of speaking different languages in a way. We've got a double angle value of cos 2x, but we do know there is some link between cot squared and cosec squared. Now, it might be useful to write down the identity for that. I'm not saying it will be useful, but it might be. So the Pythagorean identity, which is quite useful for this, if I just write it on the right-hand side, is, of course, cosec squared x, in this case, would be identical to 1 plus cot squared x. All right. Now, that's how they're related. So you'll notice that if you had cot squared x subtract 1, if we just do a bit of manipulation here, I would have to subtract 2 from both sides of this identity to get that. So that would give me cosec squared x subtract 2 would be identical to the cot squared x subtract 1. All right, so I'm not sure how useful that will be, but at least we've got a relationship. So perhaps with a bit of manipulation, the right-hand side would converge on this. All right, but I'm not sure. We'll have to wait and see. So that's one approach. We might be able to use that. The other thing we need to be aware of is the cos 2x. Now, when it's cosine, of course, there are 3 possibilities. There's 3 possible identities we need to be aware of with cosine. Let's write them down. It's always a good idea if you're not, especially if you're not familiar with them. So the first one that we derived, if you remember, was cos squared x subtract sine squared x. And then you can make substitutions using sine squared plus cos squared is 1. And you can get 2 more variations. You can get 2 cos squared x subtract 1. And you can also get the sine version, which is 1 subtract 2 sine squared x. All right. So those are things to be aware of. Now, at the moment, it's quite difficult to sort of tell which side to work on. On the right-hand side, because we have these three variations here, I mean, I could start with that, and then I could start with the top one, and that could be a dead end, and then I would have to make a substitution or start again with one of the other two. So maybe if I start with the left-hand side and see what I can do with that. Now, if you can't see a direct substitution or something that would make an instantaneous step that would make a leap forward so you can solve it quickly, if you can't see anything where you can make a substitution, a really good idea is to just break everything down into those simple building blocks, the sines and the cosines. And I think that would be a good idea here because we've got so many different things going on with obviously the cos 2x here and the cosec squared x. And we've seen that making a substitution for cosec squared might not be very beneficial. So I'm going to start with the left-hand side, and we're going to break everything down into those simple building blocks, and we'll see if we can construct the right-hand side. All right. So this is usually a good strategy. All right. But again, we're not sure at this stage. So cot squared. Now, remember, I'm going to use the fact that this is a reciprocal trig identity. I'm going to take that for granted that we can do that. So if you remember, if you use that third letter rule, which I'm just going to highlight again, it's a t, isn't it? That means this is 1 over tan squared, or more usefully in this instance, it's going to be cos squared over sine squared. So I'm going to write that first. So the substitution for cot squared is going to be cos squared x over sine squared x. All right. And maybe I should write that down as part of our summary over here. So we could write cot x is identical to cos x over sine x. I mean, you don't want to spend all day writing down a summary, but it just for your reference. Okay, and then we're going to subtract 1, and then we're going to see what we can do with this. So that's the left-hand side. Now, another thing to bear in mind is that on the left-hand side, you have two terms. You've got the cot squared and the -1. On the right-hand side, there is only one term. So that is suggesting that I need to combine what I've got here into one term. And I can do that by finding a common denominator. So that's going to be my next step. All right, I hope this is making sense. So I'm going to keep the cos squared x over sine squared x as it is. And to create the common denominator, obviously it's 1. My common denominator is going to be sine squared, isn't it? So to create the 1, I'm going to have to multiply by sine squared in the numerator. Okay, so that's come from that bit there. All right, now I can combine the two terms into one single term. So I can write this as one fraction essentially. So this is going to be cos squared x subtract sine squared x all over sine squared x. So I've got everything in terms of sine and cosine. There's nothing more I can do. Is there an identity I can use now? Because we don't have cosec or cos 2x. So let's have a look. Right. Now, this is where we get a bit more excited. So you'll notice we've got the cos squared x subtract the sine squared x here. And I can replace that with cos 2x, which is exactly what I wanted. Okay, so I'll do that first. So we've essentially got cos 2x. Show that I've actually made a substitution. So this is going to be cos 2x. That's divided by the sine squared x. And an alternative way of thinking about this would be, well, this is cos 2x multiplied by 1 over sine squared x. Now then, right, this is promising. If we look at the third letter rule again, but this time on the right-hand side, for cosec, that tells me cosec squared is 1 over sine squared. So we've actually got the answer. It's staring at us. So I can now just write down the answer. This is just the same as cos of 2x multiplied by cosec squared x, which is the right-hand side. And remember, I'm not allowed to manipulate the identity in any way. I have to stick to the one side and show that it is indeed equal to the other side. Okay, now that's just one way of doing it. Okay, there are more ways of doing it, I'm sure. Okay, that's just one approach. If you want to, if you've got space, perhaps try it. You're starting with the right-hand side and try and show that the left-hand side is indeed cot squared subtract 1. Okay, but I'll leave that there. That can be an exercise for you. Now, moving on to worked example 2, I've put a little asterisk next to this because this one is quite challenging. So what we have here, we've got a left-hand side, which is purely in terms of those building blocks, isn't it? Cosine and sine. So that's kind of pushing me away. I think I want to leave that as it is. Maybe that's something we can show. So perhaps we're going to start working on the right-hand side here with these reciprocal trig functions that I know I can write in terms of sine and cosine. So that might be a good way just to get us started. I don't think there's any need to do any kind of reverse engineering on the opposite side, on the left-hand side. I think we just need to sort of make those substitutions and see where that takes us. So let's have a look at the right-hand side this time. And notice as well, there's nothing squared, there's no double angles, so there's no need to write any of that down. We just need to be aware of what cosec and cot actually can be converted into. So we can see that we've got the third letter rule going there. So we know cosec is, of course, 1 over sine, and cot usually is 1 over tan, but because I want to be dealing with coses and sines, I can write it as cos over sine. So that's what I'm going to do. So for the first bit, we're going to say, okay, the right-hand side is going to be exactly the same as 1 over, and I'll make the first substitution for cosec, which is, of course, 1 over sine theta, right there. And then I'm going to add cot, and I'll do this one in red. So this is, of course, cos theta over sine theta, like that. Okay, so I've just made my substitutions. Now, this makes a rather ugly looking fraction. There's nothing worse than seeing fractions inside fractions, but we have some advantage here. We've got a situation where we've got the same denominator in both of these nested fractions. So we've got sine theta in both denominators. If I multiply the entire fraction by sine theta, so if I multiply the numerator by sine theta and the denominator by sine theta, and by the denominator, of course, I mean the whole thing, that will hopefully clear the fractions within the fractions. So that will be my next step. I want to make this look a bit more simple. So in the numerator, of course, I'm just going to get sine theta on the top. All right. And in the denominator, if I clear the sine thetas, I'm going to get 1 for the first one plus cos theta. And you might think, well, there's nothing more I can do here. And the problem is, of course, it doesn't look like the left-hand side. It's reciprocated, and there is also a sign issue. We have a positive instead of a negative between the 1 and the cos theta. So the question is, what do we do? I really desperately need to get a 1 subtract cos theta into that numerator somehow, because that's what it says. It's simple as that, really. I have to get that in there. All right. The only sensible thing I can do, there's no way I can make a substitution with this sine theta here. It's just simply out of the question. We've got everything in terms of sine and cosine, so there's no substitutions I can make now. I'm simply going to have to multiply the numerator by the 1 subtract cos theta. And the reason is because that's the only way I can get 1 subtract cos theta into that numerator. So I'm going to do that. This is the sort of tricky bit. So I'm going to multiply the numerator by that. And that will guarantee that I'll get the 1 subtract cos theta that I want. But I'm restricted in the sense that because I'm multiplying by that, I am forced, of course, to multiply the denominator by the same thing. Otherwise, I'm changing the nature of the fraction. I'm changing the proportion. So everything in the denominator now has to be multiplied by 1 subtract cos theta. Okay, that's the important step, all right, which is why this question gets an asterisk. So let's carry on. Now I've forced the issue. What happens? Well, I'm going to get in the numerator sine theta multiplying, and I'll just leave it as it is. I'm not going to expand it or anything. 1 subtract cos theta, like that. Okay, and in the denominator, what's going on here? Well, this is where it gets interesting. We have got in the denominator 1 plus cos theta and 1 subtract cos theta. So we have the difference of 2 squares. Perhaps just make a note of this. So we've got the difference of 2 squares. Now that's going to prove crucial, isn't it? If I expand those brackets, that's going to give me, and we can do this really quickly, 1 subtract cos squared theta in the denominator. Okay, just expanding those 2 brackets. Of course, these are multiplied together. Now, if you look at the 1 subtract cos squared, again, this is why you need to be so good with your identities. What can we replace that with? Well, we can make it simpler because we can make this into just sine squared. So this is identical to sine theta multiplying 1 subtract cos theta. And in my denominator now, I'm going to have sine squared theta. Okay, now this is where it gets interesting. We've now got a situation where we have sine theta in the numerator and a sine squared theta in the denominator. We have cancellation. So the sine theta is going to cancel down to 1, and I'm going to have 1 factor of sine theta left over in the denominator. And lo and behold, there's our answer. So this is identical to 1 subtract cos theta over sine theta as required, which is, of course, the left-hand side. So I started with the right-hand side this time. It doesn't matter which side you start from, as long as you don't manipulate and cross-multiply or anything like that. Okay, so that concludes worked example 2. If you can find another way of doing it, by all means, do this as an exercise, and you can send me your solutions if you like. So now we're on to worked example 3, and probably what I should have said in previous examples, and you can do this from now on, is perhaps pause the video and try these yourself if you like doing this kind of thing. If not, just follow through the steps with me. So this one, we've got a rather complicated looking left-hand side, which suggests that might be where we want to start. And we have a right-hand side, which is simply just tan A. Now, there's a few things to consider here. Once again, we're going to need to be aware of our double angle identities. So this is a really crucial point. We have 2a and 2a on the left, okay? But notice on the right-hand side, this is no longer 2a. It's just a singular a, which means that double angle identities must be in play here. So I think we should write them down just once again, just so that we've got them handy. Okay, so I've just put my summary of my double angle identities on the right hand side there. So we might want to use those later. And let's just have a look at what we've got. Well, in the denominator on the left, I'm pretty confident I'm going to have to swap out the sine 2a with the 2 sine a cos a, which I've written down at the top of the list here. So why don't I go ahead and do that? All right, I think that's going to have to be the first step. My hand is forced, isn't it? Because there's no other way of doing this substitution. So if we start with the left-hand side, all right, so the left-hand side is going to be, well, we'll keep the 1 subtract cos 2a first in the numerator. Okay, but what I'm going to do, I'm going to swap out the denominator. So this is now going to be 2 sine a cos a, and at least I'm down to singular a's now. Okay, so this is in keeping with the right hand side, isn't it? I've got this just 1a, sine a cos a. Now then, the problem we have is that we have a choice once again of 3 possible double angle identities here to swap out in the numerator. And the question is, which one is it going to be? Well, this is where we go back to the identity itself and we do a bit of reverse engineering. We're going to work on the right hand side and just see if we can go back a couple of steps to see what the penultimate steps might be in this proof. So one of the steps that might come before the tan a would be obviously sine a over cos a. That's possible, yeah? Highly likely, in fact, if we're dealing with sine a's and cos a's everywhere. So that suggests that I would really, really like to keep a cosine a in that denominator. There, okay? I want a cosine a in the denominator, and I have a cosine a in the denominator here. All right? So that also suggests that this 2 and this sine a need to cancel out somehow. Well, if I want to cancel out a 2 and a sine a, which is the best candidate to do that? That means that I've got to have a 2 and a sine a or something similar in the numerator. All right. Now that suggests that it's the bottom one here that is going to do that job. Okay. I hope you're following that kind of reasoning. So I think that would be a good idea. If you do it wrong, of course, then you might just have to make another substitution. But we want to save time. We want to be economical with these steps, don't we? Okay, so for the left-hand side, I'm going to swap out in the numerator now. 1 subtract. Now, got to be careful with the signs here. So remember, we've got cos 2a is being subtracted from 1. So I'm going to open up some brackets like that. And I'm going to put the identity 1 subtract sine 2 sine squared a inside that. So 1 subtract 2 sine squared a, close the brackets. Okay, and that's going to be all over 2 sine a cos a. All right, now let's tidy up the numerator. So if you look carefully here, we've got the 1 subtract the 1, that's going to go. And then we also have this double negative here and here. So I'm just going to be left with 2 sine squared a in the numerator. So that's good. We'll put that in. So it's 2 sine squared a divided by 2 sine a cos A. Right, so it looks like we've got everything we need. Now we'll just check for the cancellation. Well, let's have a look carefully. We've got the 2's will obviously cancel, which is what we needed, which is good. And then I have a sine squared in the numerator. Okay, and a sine A. So we're going to drop that down by one factor of sine A. So that's going to become sine A there. And if I divide by sine A in the bottom, of course, that's just going to be 1. So that leaves me with sine A in the numerator over cos A in the denominator, which is exactly what we predicted, which is tan A, which is the right-hand side. Okay, which is correct. Now, just so you're aware, I mean, if you started with the right-hand side, your first step might be to get sine A and cos A, but you've got quite a job, haven't you, to get from cosine A to this. So it's always better to start with the more complicated looking side and break it down, go into those building blocks, the sines, the cosines, and look for cancellation. And also be very mindful of these trig identities. They are so important, okay? And in particular, this one in this case. Okay, moving on to example 4. Now, this is quite interesting. We've got a very complicated looking left-hand side. And the reason I say that, of course, is because we have these power 4s here and here. Now, notice, of course, that power 4, although slightly off-putting, it is an even power, and we're finding the difference between the cos to the power 4y and the sine to the power 4y. So this is the difference of 2 squares. And if you're not convinced by the complexity of that, I can do this with a simple substitution. So suppose we say we'll call u cos squared y. I mean, you don't have to do this, of course. This is just me explaining it. And if you call v sine squared y, then what we have on the left hand side is essentially u squared, which would give us cos to the power 4 y, okay, and also we would have v squared, which would give us the sine to the power 4 y. Okay, so it's the squaring obviously creates the power 4s. Okay, but that obviously means that the non-squared term, if you square root that, will be cos squared and sine squared, not power 4. So on the left hand side of this, so let's start and let's discuss what's going to happen. So on the left hand side, we could think of this as, well, we've got u squared subtract v squared, haven't we? So I'll use that substitution if you like. Okay, so u squared subtract v squared, because it's cos squared, I beg your pardon, it's cos to the 4y subtract sine to the 4y. Okay, plus 1. Okay, and we know this is identical to 2 cos squared y, but we're going to just work on the left-hand side. And now we can see that we've got the difference of 2 squares, haven't we? Okay, we've got u squared subtract v squared. So we can see clearly that it's the difference of 2 squareds now. So I can replace this with u plus v multiplied by u subtract v, and then that's plus 1. Okay, so that's what the left-hand side is identical to. And you don't have to do any of these steps in particular. It's just to show the abstraction. You could go straight from this part here and write down what I'm going to write down right now. Okay, so when we substitute in the u and the v, we're going to get cos squared y plus sine squared y multiplying cos squared y subtract sine squared y. All right, and then plus 1. And that's what the left-hand side is now equal to. That's applying the difference of two squares again. And again, you don't have to make a substitution if you don't want to. All right. Now then, we haven't written a summary in this instance, but if you're familiar with your identities, and again, the importance of knowing these is so important. I cannot stress it enough. We've got a famous identity there. That's just going to be 1, isn't it? All right, so I can just make a note of that. That is all identical to 1. And in the second bracket, we have cos squared subtract sine squared. Now, those of you who are familiar with your double angle identities will remember that the second one is exactly the same as cos of 2y in this instance, if we're talking about y. All right, so I can just put an identity symbol there. This is just going to be cos of 2y. It's a double angle identity. So let's write the next step. So we're going to have 1 multiplied by cos 2y. Okay, plus 1. Now, does it look like the right-hand side? Well, not yet. So now we have to consider, how do we get rid of the cos 2y and replace it with a cos squared y? Well, the answer should be obvious. Now we've done a few of these, we know we can now use the following double angle identity. So we're going to use cos of 2y is identical to 2 cos squared y subtract 1. Okay, these are the ones you need to learn. And please don't be put off by the angle changing in each question, all right? We're talking about y in this case, okay? So it's just y's all the way across. So let's make the substitution now. So in the next line, we're going to have, well, cos 2y is just going to be 2 cos squared y subtract 1, and then we obviously add the 1 on the end, and they're going to cancel. So we get 2 cos squared y, which is the same as the right-hand side. So we've finished. So there's lots of skills on show in that question. Okay, so now our level of interest is going to go up a notch. We now have a cos 4 theta, and we have some rather nasty looking powers on the left-hand side. Sorry, beg your pardon, on the right-hand side here. Cos squared is okay, but it looks like we've got some kind of polynomial in terms of cos theta. Now, ordinarily, I would say, yeah, start with the complicated side, and which would be, obviously, in this case, the right-hand side, and then show that it simplifies. I mean, we could do that, but there is a more subtle approach, and it uses the double angle identities. So notice that we have cos 4 theta here. Now, this is a double angle, okay? Clearly because 4 theta is, of course, 2 lots of 2 theta, isn't it? Okay, so it's a double angle with 2 theta being the original angle. So I could actually write the identity like this. So if I consider the left-hand side, and if you need that as just to get you started, please pause the video and have a go yourself. You know, you don't need to sit and watch me do it. You can try it yourself. I would encourage you to do that. So using the logic I've just mentioned, this is the cosine of, and we'll put that in again, 2 lots of 2 theta, isn't it? And what am I basing this on? Well, this is double angle identity. Okay. And remember, we have a choice. Let's just write up our list of double angle identities for cosine. All right. So once again, I've just spared you me writing those out. Let's have a think what's going on. So in this instance, The A that we're talking about is this 2 theta here, isn't it? Okay, it's 2 lots of 2 theta. That would create the 4 theta. So on the summary, what we've essentially got, if I write down cos of 4 theta, which is essentially what I've just been saying, and I just replace the A everywhere with 2 theta, don't I? Okay, so this would be cos squared 2 theta subtract sine squared 2 theta, or you could have 2 cos squared 2 theta subtract 1, or you could have 1 subtract 2 sine squared 2 theta. Okay, with A being the 2 theta all the way through it. Okay, all the way through. So the question is, if that's my cos 4 theta that I'm talking about, which one am I going to use? None of these look anything like this polynomial on the right hand side here. But we've got some interesting information, haven't we? This polynomial is purely in terms of theta only. Okay, there's no 2 thetas anywhere, it's just theta. All right, but I can start off by using 2 cos squared 2 theta, and perhaps I can break apart the 2 theta and start to use cos theta, can't say it, cos thetas all the way through. So I think we'll start with that. I think that's a good place to start. Get everything in terms of cosine first. So back to our identity. So this is going to be identical to 2 cos squared, and just to emphasize this, 2 theta, okay, subtract 1. That's where you've got to be careful. Now we've got the 2 theta, we can again use the double angle identities, because we can now consider A as just theta now, okay? So we can use the double angle identities again. So just to make a note, just make a new list of cosine double angle identities. So cos 2 theta, of course, would be cos squared theta subtract sine squared theta. All right. Or you could have 2 cos squared theta subtract 1. Or you could have 1 subtract 2 sine squared theta. Now, the important thing I'm sorry for writing it out again, but this is an important step. What we've got to consider here is that it's cos squared 2 theta. So all this is squared, and that's what gives you the cos squared 2 theta. Okay, remember the squared goes after the s, so there's no confusion with the angle. So that's cos squared 2 theta. Now, if that's the case, I would then have to square any one of these. All right, but I have to also choose which one I'm going to use. And because it's cos squared 2 theta, and because I want everything in terms of cos theta, I think the one to choose, and you should be screaming at the screen with me, it's going to be that middle one. All right, so I'm going to replace the cos squared 2 theta here with this again. Okay, let's do that. So this is going to be identical to 2, and I'm going to open big brackets here. And I'm going to have to square the 2 cos squared theta subtract 1. All squared. I'm just going to put that in a big bracket, okay? And then I'm going to subtract 1 on the end. Right, now, whatever happens, I'm definitely going to have, I could make a mistake here, but I'm definitely going to have terms purely in terms of cos theta, which is what I want. So there shouldn't be any more substituting now. It'd just be a case of expanding and simplifying. So let's have a go. I'm just going to move the identity across because we might need a bit more space here. Back to the big square brackets. And I'm just going to expand carefully the two brackets inside the big square brackets. So we're going to have 2 cos squared theta, subtract 1, multiplied by itself. Not cutting any corners with this. All right. And then we're going to subtract 1 on the end. Okay. Right, now let's tidy up inside the green bracket. So this is going to be 2, big green bracket again, and we'll do this in one step, but this will be fine. So we're going to have 4 cos to the power 4 theta. Okay. Subtract. Now there's going to be 2 lots of minus 2 cos squared theta, so that's going to be subtract 4 cos squared theta. Just be very careful with the powers here. Okay, and then that's going to be a plus 1. All right, and then we close the big green brackets, and then we subtract 1 off the end. I should have done that in blue in the previous step, but never mind. All right, now let's multiply it out. So this is going to be 8 cos to the power 4 theta. Okay, subtract 8 cos squared theta plus 2, and then again subtract the 1, and there we have it. So I think we've got the final expression now. So this is 8 cos to the 4 theta, subtract 8 cos squared theta plus 1. So for questions like this, it's a bit like when you're working out the sine or cosine of 3 theta. You use the double angle identities carefully, and you'll look on the right hand side. What is everything in terms of? Well, it's all in terms of cos theta. So you make substitutions until you get everything in terms of those cos thetas, and then expand and simplify. All right, so that concludes worked example 5. All right, so we've had quite a few examples in this lesson, and we have one more just to give you a broad idea of the different sort of flavors of questions you can get. So we're going to have a look at this, and again, we have a very, very complex looking identity, in particular on the left-hand side. But you'll notice we have the same issue as we had in worked example 4. We have the difference of 2 squareds, and it's even more apparent in this situation. So if I use that same format just to go over it again, if we said, for example, let u equal the cosine of a subtract b, and v would be the cosine of a plus b, then we can see on the left-hand side, we have u squared subtract v squared. And in fact, we'll start off our proof in that fashion. So on the left-hand side, and remember, I'm starting with this because it looks the most complex, okay? It looks like I can do something with this. So on the left-hand side, I have u squared subtract v squared. All right. And granted, I know that there are double angles on the right-hand side with 2a and 2b, but when you have sums and differences of angles on the left, I think that trumps the double angles in terms of complexity here. All right. So we're gonna focus on the left-hand side. So we have u squared subtract v squared. Let's immediately write that as the difference of 2 squares factorized. So that's going to be u plus v multiplied by u subtract v. And once again, if you're happy with the level of abstraction, you can just go straight to the next step. You don't have to make the substitution like I've just made. But just be aware there's a complicated substitution that's taken place. So I'm going to use large square brackets here. And inside the square brackets, we're going to have the cosine of a subtract b and then we're going to add the cosine of a plus b, which are u and v respectively. Okay, and that's just the first bracket. So just to be really clear, everything in here represents everything here, just u plus v. Okay, so I'm now going to multiply that by u subtract v. So we'll do that now. So I'll put a multiplication symbol in as well. Why not? Multiplied by, and we'll put everything in again. So this is going to be the cosine of a subtract b subtract the cosine of a plus b. Okay. There we go. Now, what can we do here? Well, we don't have the squareds anymore, but remember, we've got compound angle formulae that we can use. They're at our disposal. Let's just summarize them up here on the right-hand side. So if you remember, and these are in the formula book, but again, I would strongly urge you to learn them. Cos of a plus b is identical to cos a cos b subtract sine a sine b. Okay, remember the signs in the middle are opposite. Is a crude way of putting it, but it's true. Okay, and then when we have the cosine of a subtract b, we simply change the sign to a positive. So this is going to be cos a cos b added to sine a sine b. Okay, and we'll substitute those in all the way across this product. So this is going to be a big step. Right, so I've just written out that next step. It's a bit of a mammoth step, isn't it? I'll just explain it, and while you copy it down, you might just want to pause the video just to get that down. So we have the cos a, the cos a cos b plus sine a sine b. These obviously correspond, both of these, that they appear twice, that I did it in orange. Okay, they obviously correspond to this, the cos of a subtract b, which is the first term in the brackets in the second step that I highlighted in purple, and then obviously on the right hand side of each bracket we've got the cosine of a plus b, which has the negative sign inside it. So I'll just highlight that as well. So this expression here and this expression here correspond to this. All right, and you notice we have to be careful because we have a subtraction in that second bracket, which I've got here. So I've got to subtract the whole of that second expression. So that's why I've used the brackets. It's extremely important that you do that. So it rather a nasty looking piece of algebra there, but we should have some simplification now. We're only going to end up with sine 2a, sine 2b. So let's see what happens. Now, we've got an addition, but because we've got positives and negatives, there should be some cancelling going on here. Right. So if we look at the first bracket, we'll call this bracket 1 here. The first pair of green brackets. We double up on the cos A, cos B. So they're going to be added together. So I can write this as part of my next step. So I'm going to have two lots of cos A, cos B from my first bracket. And I better just keep that big square bracket there. But if you'll notice, for the next bit, we've got a plus sine A, sine B, and minus sine A sine B. So they will just simply cancel. Okay, so there's no more of that. So that's the first bracket simplified, which is rather nice. So we've got 2 cos A cos B like that. So we can close that, and then we're going to multiply this by whatever happens to the second bracket. So again, I'll put the big square green brackets there. Now then, in the second bracket, we've got the opposite going on. Essentially, we've got a positive cos A, cos B, but because we have a negative outside the bracket, that means this is going to become negative. So we have cancellation here and here. So they're gone. All right. But also, we've got the plus sine A, sine B here, and we've got a negative sine A, sine B here, but we also have a negative on the outside of the bracket. So that makes that a positive. So we're going to double up now on the sine A, sine B. I hope I'm not confused you with all the colors. So simply just check in your own working that you agree with that. Okay, you could put an extra step in if you like as well. In fact, why don't I do that just to make absolutely clear what's going on? So you would end up with cos A, cos B plus sine A, sine B. And then when you subtract the whole bracket, you would be subtracting cos A, cos B. But you would be adding the sine A, sine B because of the negative sign outside of the bracket. So maybe that's more clear. Okay, and now we've seen that. We've got two lots of sine A, sine B, and the cos A, cos B's cancel. So we'll put those inside our second green bracket. So we're going to have 2 sine A, sine B. Okay. So what we could effectively do is write this as one gigantic product with sine A, sine B, cos A, cos B, and then the two 2's make 4. But if we just go back to our original problem, on the right-hand side, you can see that we've got sine 2A and we've got also sine of 2B. So it might be a good idea just to jot down what those identities actually look like. So I'm going to write those in my summary up here. So sine of 2A would just be identical to 2 sine A cos A, and similarly sine 2B is simply going to be 2 sine B cos B. And you'll notice from the brackets, I can show this really clearly just by putting my factors, my cos A's and cos B's, sine A's and sine B's, in a particular order. So it really just shows, it emphasizes that we've got sine A, sine 2A and sine 2B multiplied together. So let's do that. So we'll keep the 2's as separate factors. We won't multiply them together to make 4. So if I want sine 2A, that's simply going to be 2 sine A cos A. And let's just have a look what I've just used up from the previous step. Well, I've used up a 2. I've used that one up. And I've used up the sine A, and I've used up the cos A. So that's all been used. And then if I put a multiplication symbol here, I need another 2. Okay, and then I've got a sine B and a cos B left over. So there is absolutely no doubt that this is indeed sine of 2A multiplied by the sine of 2B, okay, which is the right-hand side. So that concludes the proof, and that concludes the lesson.